What I want you to do next is consider a sum. How about the first item be A, and I'll have the second item be A. Oh, you know what? It's not going to work. I don't mean to imply they're all the same. So let me change things a little bit. Let me take something called a sub 1, add it to a sub 2, add it to a sub 3, add it to dot, 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 all the way down to a sub n. So dot, dot, dot notation simply means I'm not showing all the intermediate terms, but in the end I've got n of them. Now, notational speaking, I will refer to this as a sum, but I'll steal the uppercase Greek letter sigma to represent a sum of an a sub I as I range from 1 to n. I hate to say it's so elementary because technically speaking, you've already studied sums and summation notation back in pre-calculus, but just jog your memory. Some properties, which I can spell, I really can. Number one, if you're going to sum together, maybe something like a constant added to itself n times. Isn't that just this? But back in elementary school, we replaced repeated addition with multiplication by natural numbers. So isn't this just simply c times n? There's one property I need. A second property, I'm summing together as I arrange from 1 to n a bunch of things referred to as a sub I like I did before, but each and every one of them being multiplied by a constant. So if each and every one of these is being multiplied by a constant, then can't I use an exaggerated version of my property of distribution of multiplication over addition? Meaning I can pull the c out and simply have at the end the constant times the sum as I arrange from 1 to n of a sub I. Now I do think if I have a sum like this, I can break it up. Justification is trivial. Let's look at the addition. If I have this, isn't that this? But now I do think with the addition property, these parentheses are superfluous. So if I just add these terms in a different order, I get exactly what I want. Maybe more important, I need these formulas in my back pocket. So you're not going to be able to get away not knowing these formulas. I won't discuss this one because that's on the other side of the board. That was trivial. It's just repeated addition. Now, as far as this one's concerned, to justify it, how about if I do this? Okay, everybody, board space again. These 1, 2, 3, 4 statements are true for all natural numbers n. But the phrase for all natural numbers n is getting in my way, so it's just understood that I have that in there at this point. As far as the first one's concerned, sorry, I misspoke. As far as the second one's concerned, actually, I'll say that again. I'll write it backwards. Now, if I take these two equations and add them together, here's what I get on the left-hand side. Now, on the right-hand side, notice how in the first column, this adds up to an n plus 1. But in the second column, that adds up to an n plus 1. The last column adds up to an n plus 1. Second to last column adds up to the same thing. All the columns add up to n plus 1. But the number of columns I have is n of them. And if I divide both sides by 2, that's what I get. Now, I could have proven this statement with mathematical induction. I didn't. So let me use mathematical induction to drive the proof of the third one. Now, I'm expecting you to know mathematical induction as a technique of proof writing. It's something you did indeed study back in pre-calculus. Or maybe here it's their college, you studied it in college algebra. So here I go. To prove the statement is true for all natural numbers n, part 1, we have to show it is true for the smallest possible value for n, which is 1. This part of the proof is always, I shouldn't say always, for now anyways, almost always a complete waste of time because it's so trivial. I'm going to write both sides where n is equal to 1 and see if I can't come in and bridge the gap. On the left-hand side, if n is equal to 1, this is what I have. On the right-hand side, if n is equal to 1, this is what I have. Sorry, is that too small? My goodness. Now, on the left-hand side, that gives me 1 squared added to nothing else because the starting value for the index variable I is the same as the last value. But that's just equal to 1. But over here, doesn't that give me a 6 over 6, which is also equal to 1? So, trivially, this statement is true when n is equal to 1. So part 2 is where all the work is, as you recall. Again, I'm using the technique of mathematical induction as a proof writing technique. So part 2, let's assume this statement right here is true for some natural number n. I'll call it k. We will show that this statement right here is true for the next value of n. Well, the next value of n is 1 beyond k, it's just k plus 1. So we'll show that this is true when I replace n with a k plus 1. So we'll show that as I ranges from 1 to k plus 1 of my I squared is equal to what you see on the right-hand side with every n replaced with a k plus 1. Now that's what I'm trying to show. That's why I put it in parentheses. And again, because of board space I have, I can't, I need to do something to save myself some space. So since this is what I'm trying to show and you're able to write it down, I'm going to erase it and use the space. But just like in verifying a trigonometric identity, if I'm trying to show equality holds, then I better start with one side and mathematically deduce this equal to the expression on the other side. But somewhere along the way, I will be using my inductive hypothesis. That's a really big word, the word if or assume. Whenever I see that, I can replace it with that. So what I'm about to erase, this equation right here, is what I'm trying to verify. So let's talk about the sum of I squared as I ranges from here to here. Isn't that just this? Down to the last term, k plus 1 squared. But notice its predecessor is just k squared. And if you take a peek at the first k terms, isn't that just this? Oh, then I got the lingering term out here, outside the sum. But again, you saw this expression somewhere within my inductive hypothesis. So exploiting my inductive hypothesis, that gives me this. Now, I know I erased the equation we're trying to show. It's true that this is equal to other junk, but the other junk was a single fraction. This is not. So I'll just combine fractions. Pulling out a factor k plus 1 from the two terms, here's what's left over. Now, it looks to me like I've got a fraction whose denominator is 6, whose numerator is k plus 1 times something. Let's talk about the something. Is that going to be this? And it looks to me like that trinomial probably factors further. Now upstairs, here's my first factor. Here's my second. Oh, my goodness. Here's my second. My third could be expressed as this. But that 2k plus 2 can be expressed as such, which is exactly what I wanted. Therefore, indeed, it is true, and I just have proven that the sum of the first n squared natural numbers is indeed equal to this expression. Not sometimes, but for all natural numbers n. I've just proven what I want to show. Now, we are going to use these. I'll leave that for this one for you to prove. And of course, you'll be using mathematical induction for that as well.